Okay, meine Kleinen, um, let us talk today a little bit about, or not a little bit, a lot about some titration. And specifically, I want to talk about weak acid, strong base titration. And what do I mean by that? I mean we have a weak acid, and we'll call it HF, and that it is in an Erlenmeyer flask, and that we have a burette, and in that burette I have hydroxide, sodium hydroxide, and we are dropping it in here. We'll probably have an indicator here uh, like methyl red. Methyl red? Yeah, I think that might go. Let's see, my pH is going to be around. No, phenolphthalein would work just fine. Yeah, phenolphthalein, phthalene would work just fine. We need some kind of indicator, right? And we are going to slowly add this hydroxide until we get beyond the equivalence point. Now, the first place to start, I guess, is what do we mean by an equivalence point? What is an equivalence point? Well, the equivalence point is the point where the hydronium, or you can think H plus, from my weak acid is equal to the moles of hydroxide added. All right. What that means is all of the first hydrogen in a weak acid, and in this case there's only one hydrogen, the moles of hydrogen here have been completely reacted with the moles of hydroxide. Got it? So that is at the equivalence point. Now, think about this for a second. I have HF plus OH minus, and what's that going to form? Well, it's going to form hydroxide, no, it doesn't, water, and F minus. Now, let's say that initially I start off with 1 mole of HF. Well, how many moles of hydroxide is it going to take to react with all that 1 mole of HF? Well, 1 mole. Why? Because there's a 1-to-1 ratio. And we're going to start with 0, 0. So I'm going to add 1 mole of hydroxide. What's my change going to be? Well, this is going to be a minus 1 mole. All that hydroxide will react. All of this HF will react. What do I make? I make a mole of water. And I make what? 1 mole of HF. And at the end or final, whatever you want to say, I have 0 HF left. I have 0 hydroxide left. We don't care about the water, but I do have 1 mole of F minus left. So, at my equivalence point, at the equivalence point in a titration of a strong base by a weak acid, what do I have left? I have a weak base. Got it? So I have a weak base. If it's a weak base, what's my pH going to be? Well, if it's a weak base, that pH is going to be greater than 7. Now let's talk for a minute about how do I determine the liters? How do I figure out the volume of my hydroxide needed to reach the equivalence point? All right. So to determine volume of strong base to reach equivalence point, what am I going to do? Number one, I'm going to calculate the moles of my, I'm going to go with HA for my weak acid. I'm going to calculate the moles of my weak acid. Got it? And how am I going to do that? That's going to be equal to the liters of my weak acid times the concentration of my weak acid. Good. Number two, I know then that the moles of my hydroxide equal the moles of my weak acid. Why? By definition, right here. At the equivalence point, those moles of hydroxide added equal the moles of hydronium coming from my weak acid. Good. Now the third thing, and you might think this is silly, but it's not. What if we have to be careful? We want to make sure that the moles of my strong base, we're going to come up with moles of my strong base, which is equal to the moles of my hydroxide times the mole ratio between hydroxide and my strong base, right? So I could have moles of strong base per moles of hydroxide. Usually, ladies and gentlemen, this is 1, right? This is a 1-to-1 ratio, moles of hydroxide to moles of strong base for things like KOH, NaOH. But why do I tell you this? What if you come up with something like barium hydroxide? Well, then what? I don't have a 1-to-1 ratio, so I have to always be careful. I can't assume that moles of hydroxide equal moles of strong base. I have to look at that subscript and put it into my mole ratio here, right? In the case of barium, this would be a 2-to-1. In the case of sodium hydroxide, it's 1-to-1. Okay, then once I have my moles of strong base, I can calculate my liters. Liters of strong base equal moles of strong base divided by the molarity of strong base. All right, good. So let us do that right now. Let's go to a problem. Zoink. And let's look at this problem. We're going to titrate 25 milliliters of 0.1 molar HF with 0.05 molar sodium hydroxide. What's the volume of hydroxide necessary, sodium hydroxide, to reach the equivalence point? Okay, what's our process? Number 1, let's get moles of my weak acid, 0.025 liters times 0.10 molar, and that gives me a 0.0025 moles of hydronium. We know that moles of hydroxide equal the moles of my weak acid at the equivalence point. So at EQPT, the moles of hydroxide equal the moles of my weak acid, which will equal 0.0025 moles. Wunderbar. Now we want to get moles of sodium hydroxide, which is equal to moles of hydroxide times, what's my mole ratio in sodium hydroxide? Well, it's 1 mole of sodium hydroxide per 1 mole of hydroxide. Yeah, that's pretty easy. So this is equal to what? 0.0025 moles of sodium hydroxide. Now, I can get liters of sodium hydroxide, which will be equal to my moles of sodium hydroxide per the concentration of my sodium hydroxide. So this will be equal to 0.0025 divided by, what's that concentration? 0.050 molar. And when you run this number out, you get what looks to me like a 0.050 liters, which is equal to 50 milliliters. Great. Okay, we've taken care of the first question. Now, let's go to the next. I think we need to discuss some more stuff. Ooh, okay, so here we go. We've got our beautiful titration here, and we're going to keep coming back to here, right? Very simple. So now let's do some erasing here. There we go. What do I get at the beginning? Let's say I start off with 1 mole of this. I add none of that. I have none of that, and I have none of that. What do I have? Well, if I haven't added any hydroxide, the only thing I have is a weak acid. Okay, so let's get rid of all this beautiful stuff here. Get rid of that. So at the beginning, 0 mLs of strong base added. What do I have? Added, not acted. Added. What do I have? The only thing I have is my weak acid. So if I have a weak acid, we've learned this. How do we get the pH for the weak acid? We do ice, right? We're going to use ice. And here, let's change this to more generic thing. We'll call this HA, and this will be A minus. There we go. So we're going to use ice. And when we use ice, we're going to do all the stuff, you know, minus X, 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 X. initial concentration minus X. We're going to assume that X is much, much smaller, the initial concentration. And when you do that, what do we always get? We always get the hydronium concentration is equal to the square root of Ka times your initial weak acid concentration. So how is it that I calculate my pH? Here's my steps. So number one, we're going to use ice and assume X is much, much smaller than my initial weak acid concentration. And if you do that, we find out that the hydronium concentration is equal to the square root of Ka times my initial weak acid concentration. Step 2, pH equals the negative log of my hydronium concentration. That's all there is to it. Got it? We should be good at that from the last chapter. Let's go back and let's do this in real life. So here we go. 0 strong base has been added, so that means I only have HF. We need to know the Ka for HF, right? So the Ka for HF is equal to 6.4, I believe. Let me check my handy-dandy sheet. Nope, 6.8 times 10 to the minus 4th. 6.8 times 10 to the minus 4th. And that is the Ka for HF. So my hydronium concentration is equal to the square root of 6.8 times 10 to the minus 4th times, so it's my initial concentration, 0.10 molar, and I get a beautiful number. Where's my handy dandy TI? Here we go, everyone. 6.8 e to the negative 4 times 0.1, yeah, equals, and always remember to do what? Take the square root, 8.24 times 10 to the minus 3rd. And so when I take the negative log of that, my pH is equal to, yoink, 2.08, right? I had 2 sigs here, so I can only have 2 sigs here, which means I have 2 decimals in my pH. So that is my initial pH. At 0, my pH is 2.4. Well, we look next at 10. And hey, what do we know about 50? I think we did something with 50. Oh yeah, we calculated that 50 is my equivalence point. So this is at the equivalence point. Okay, so we really want to know, what do I do if I have some strong base added, but it's before the equivalence point? Well, let's discuss that. So we come back to our page here. What happens now? Let's clean this up a little bit. Woo! Yeah, great. Almost a perfect erasure. Ah, good. So I start adding my hydroxide, right? So let's go back, and I have my weak acid, and I'm adding hydroxide. And what am I going to form? Well, we know it's HOH plus A minus my conjugate base. So let's say I start off with 1 mole, and I add 0.1 mole of hydroxide. So I'm adding some, but I'm not at my equivalence point, right? And my change then will be what? All of my hydroxide will react. How much of my weak acid will react? Well, the same amount of that, just the amount of hydroxide that is added. And what will we form? 0.1 moles of, we get water, of course, but we don't care about water right now. We get 0.1 moles of my conjugate base. And so when I look at my final, what do I have? I have 0.9 moles of my weak acid, and I have 0 hydroxide, and I have 0.1 moles of my conjugate base. So what do I have? I have a weak acid and its conjugate base. What do we call a mixture of a weak acid with its conjugate base? We call that a buffer. So when we are between, when you are between 0 and strong base added. When the amount of strong base added is between 0 and the equivalence point, you have a buffer solution. Now, do you guys remember the steps for determining the pH of a buffer solution? Well, maybe you do, maybe you don't. So first, let me tell you the steps. Here are the steps. Number 1, we want to calculate moles of HA original. Well, that's easy, right? How do I get that? That's equal to my volume of HA times the concentration of HA. All right, and we've done that really. When you calculated the equivalence point, you made that calculation. Number 2, we need to figure out how many moles of HA remain. How many remain after we added our hydroxide? Well, what are we going to do? We're going to take the moles of my HH original. Well, and then what did we add? Well, we added hydroxide, and that hydroxide reacted, right? So we're going to then subtract the moles of hydroxide added. Does that make sense? Right. Here we go. Here's my original. Here are the moles of hydroxide added, and that gives me the moles of my weak acid which remain. Yes, so we take the original weak acid, subtract the moles of hydroxide added. Number 3, we want to get the moles of my conjugate base created, right? Well, that's going to be equal to what? If we look up here, it's very simple. The moles of my conjugate base are equal to what? The moles of my hydroxide added. So moles of conjugate base equal moles of hydroxide added. Good. And you guys know how to get moles of hydroxide added? Well, moles of hydroxide added, just to make sure, it's going to be what? The the liters of hydroxide, the liters of my strong base added times the concentration of my strong base times the ratio, right? Moles of hydroxide per mole of strong base. That's how I get my hydroxide added. Good. Once I have all of this, what do? I am going to use my equation. I'm going to use ice. I'm going to assume x is much, much smaller. And what do I get out of that? From that, I get my hydronium concentration is equal to Ka and moles of my HA over moles of A minus. Now, usually we put here what? Concentration. But since these are the same, they're in the same liquid, their volumes are the same, so the volumes are canceled out. So we can just go with this equation. And we have the moles of HA, right? My moles of HA are here. Really, it's moles of HA remaining. Where do I get my moles of A minus? Well, the moles of A minus are right here. There we go. That's it. Let's go back and let's work it. Zoink. All right, we have 10 milliliters. So we're going to work this right here. I have 10 milliliters of hydroxide added. So we want to get the moles of HF, here, remaining, which is going to be my original moles. What were my original moles? Right here are my original moles of HF. So this is 0.0025. And how did I get that? Just in case you forgot, liters times concentration of HF, right? So that's moles minus how many moles of hydroxide were added? Well, we have 0.010 liters times, what's my concentration? My concentration is 0.050 concentration of sodium hydroxide times what? 1 mole of hydroxide per 1 mole of sodium hydroxide, right? Now, most of you can see that and don't have to set that up, but I want you to understand my logic completely. So I have 0.0025 minus 0.01 times 0.05 times 1 over 1, and I get 0.002, and that's going to be what, 20 moles of HF remaining. How many moles of A minus do I have? Well, that's equal to the moles of my hydroxide added, which is equal to this stuff right there, right? 0.010 liters times 0.050 molar, and 1 over 1 we're not going to mess with. Okay, so that's going to be 0.01 times 0.05, and I get 0.0005, 2 sig figs, right? Moles of F minus. F minus, we're dealing with fluoride now, right? Good. Then what do we do? Okay, we're going to use our equation to get the hydronium, which is equal to Ka concentration, or moles of my HF over moles of my F minus. So this will be equal to 6.8 times 10 to the minus fourth, which is my Ka. What are the moles of my HF which remain? 0.0020 moles. What are the moles of my F minus? 0.00050 moles. Okay, so I take that, divide that by that, equals that, inverse that, times 6.8 times 10 to the minus 4, and I get something along the lines of 2.72 times 10 to the minus third. Take the negative log of that, and I get my pH equals 2.57. All right, so that's how I got my pH there. Third place. No. Where are we? You're at the equivalence point. Okay, let's go back and talk about how is it that we calculate. How is it that we calculate pH at the equivalence point? Oh man, didn't erase everything. Oh, there we go. Jen, sorry about that. I know if I leave that up that way, you'll go crazy, which sometimes I like having happen. Okay, zoink. So let's go back. I have my HA plus OH minus, and I end up with HOH plus A minus. And we said if I started off with 1 mole of this, and I have 1 mole of this, what's the change going to be? Well, that's going to be a minus 1 mole. This is a minus 1 mole. This is going to be a plus 1 mole. And what do we have left at the end? Finally, I have 0, 0, and I have 1 mole of A minus, meaning at my equivalence point, all I have is my weak base. So then what's my process? Number 1, we need to get the moles of my weak base. And how am I going to do that? Well, that's simple. The moles of the weak base are going to equal the moles of your weak acid original, because all of the weak acid was reacted with your hydroxide, right? Oh, okay, that's a piece of cake. Number 2 now, here's where we have to be careful. We need to get the concentration of that. Well, that means I'm going to take the moles of my weak base, and I have to divide it by my total volume. Now, what is the total volume? Well, the total volume is going to be the volume of my weak acid plus the volume of my strong base added at the equivalence point. Good. And then once I have that, I'm going to use ice. Oh, I can't use ice yet. I'm going to set up ice. I'm going to use ice. I'm going to assume that X is much, much smaller. And when I do that for a weak base, remember this is ice for a weak base, I'm going to get the concentration of my hydroxide is equal to the K square root KB initial concentration, or excuse me, the concentration of my weak base. Got it? But here's the kicker. I don't have a KB, do I? I have a Ka, which means I have to go back and remember that Kb for A minus is equal to Kw divided by Ka of my weak acid. So you have to go in and calculate a Kb, plug that in here, plug this value, yoink, in here, take the square root, and that'll give you your hydroxide. From your hydroxide, then what are we going to do? Well, then I'm going to get POH, which will be equal to the negative log of my hydroxide concentration. And finally, I'll get pH, which is 14 minus my POH. Mamma mia! What kind of a question are you giving us here? Well, this is fun, right? Let's answer this then. I'm at my equivalence point. Let's get rid of that beautiful piece of work. A masterpiece. And let's just answer my question right here. Good. We have calculated that 50 mils is my equivalence point. My moles of conjugate base equal the moles of, excuse me, we're working with F minus now, aren't we? HF original, which is equal to that 0.0025 moles. Wait, where did that come from? We calculated that in step 1, right? Right here. We calculated the moles of my HF original. So we can keep using that value. So here it is. That's how many moles of F minus I have. What is my concentration of F minus? Well, it's going to be equal to my moles, 0.0025 moles, divided by what? My total volume. Well, first of all, I have 50 mils of my strong base, 0.050 liters, plus how much of my weak acid did I start with? 25 mils, which is 0.025 liters. Let's run the numbers. So I take my 0.0025 divided by quantity, 0.05 plus 0.025, yoink, yoink. And it looks to me like I get 3.33 times 10 to the minus third. That's molar F minus. Now the next thing I have to do is get my Kb, which is equal to 1.0 times 10 to the minus 14th divided by my Ka, 6.8 times 10 to the minus 4th, right? So 1 times 10 to the minus 14th divided by 6.8 times 10 to the minus 4th. Woo-wee! And I get 1.47 times 10 to the minus 12th. That's a tiny number. Let's make sure I did that right. 1 times 10 to the minus 14th divided by 6.8 times 10 to the minus 4th. Yes. Now, I want to say that my hydroxide is equal to, and this is the outcome of ice, right? Kb times my initial concentration of F minus. So this is equal to the square root of 1.47 times 10 to the minus 12th times my concentration of F, yoink, which is 3.33 times 10 to the minus third. Times, recall 1 equals, make sure you take that square root, yoink, and I get something along the lines of 7.00 times 10 to the minus ninth. So then we get the what? POH, because this is pH, because that's hydroxide, take the negative log of that number, and I get 6.15, and then add that to 14, and my pH is equal to 7.85. So that is my pH at the equivalence point. And then finally, what do we do beyond the equivalence point? What do I have beyond the equivalence point? What do I have beyond the equivalence point? So if I didn't have 1 mole, I added 5 moles. And then how much of that 5 moles would react 1 mole of that? And what would be left? Finally, 0, 4, and 1 mole. So what do I have left? I have hydroxide, and I have A minus, my conjugate base. Now, turns out that this hydroxide overwhelms the pH contribution of my conjugate base, so we essentially ignore it and just focus on the hydroxide. So here's the process. Number one, we want to know moles of hydroxide which we have left over or remaining, which will be equal to the moles of hydroxide added minus the moles of my HA original. Now, how do I get my moles of hydroxide added? This is going to be, like we've talked about before, this is going to be liters of my strong base times concentration of my strong base times the mole ratio between hydroxide and my strong base, right? That's how we get this value, in case you are a little confused on that. Let's run the oops, not running the numbers yet. All right, so that's how I get my moles of hydroxide. Then I need to get the concentration of my hydroxide remaining, which is equal to the moles of my hydroxide remaining divided by what? Total volume, right? And then from that, number 3, I can calculate my pOH. And then number 4, I can calculate my pH. Got it. All right, let's run the numbers. Do, 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 do. Do, 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 do. Do, 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 do. All right, here we go. Let's see. Let's clean this up a little bit first. Magic finger. Woohoo! And we're talking about 60 mils of hydroxide added. So we want moles of hydroxide remaining. Well, that's going to be 0.060 liters times 0.050 molar times 1 mole of hydroxide per 1 mole of sodium hydroxide minus my HF original. Remember, all from up here, my HF original, zoink, 0.0025 moles. And what do we get? So I'll take 0.06 times 0.05 gives me that, and I must subtract 0.0025 gives me that, and I get 5 times 10 to the negative, no, that's not right. Is it? 0.06 times 0.05 equals that, minus 0.0025. That's a strange number. Times 10 to the minus 4th, which is 5 times 10 to the minus 4th. Got it? And that is moles of hydroxide remaining. Good. Then we want to get concentration of hydroxide remaining, which will be equal to 5 times 10 to the minus 4th moles divided by my total volume, 0.060 plus 0.025, right? So 5 times 10 to the minus 4th divided by quantity 0.060 plus 0.025, and I get something like 5.88 times 10 to the minus 3rd moles of what? Hydroxide, right? And then I want to get my, that's not moles, sorry, that is my molarity of hydroxide. Then I can get my pOH, take the negative log, which is 2.23, and then I can get my pH by subtracting that from 14 plus 14, and voila, 11.8. Got it. I had 1 sig fig here, so I could only have 1 decimal here, so I could only have 1 decimal there. 11.8, and that would be the answer. Whoo-wee! How much time have we used up on that? Oh, this is a long one. Okay, I'm going to leave you right here. I'll tell you what, I'm going to pause, let you work on the other question. I'll put the answers up, and bye. Yeah, I guess that was a little confusing. Here's what I mean. Let us come here and You work on this one. When you have your answers, turn me back on and I'll tell you the answers. Okay, bye. Oops, I guess you need some more information, don't you? Here, let me tell you that the Ka is equal to 1.8 times 10 to the minus fifth. That's the Ka for acetic acid. Okay, now I'll give you some time to work this out. Okay, it's probably taking you about 20 minutes or so, but let me tell you the answers. Here we go. How many milliliters of hydroxide are required to reach? How about 67 milliliters, right? What's the pH? I got the pH equal to 8.84. At 0, 2.72. At 50, 5.22, and at 70, I got 11.6. I hope you guys all got the same thing I did, and if not, let me know. Okay, thank you very much, folks. Bye-bye.